It's like those devices for truckers.
Fall asleep the entire thing.
You start to fall asleep and the chair goes round
in your space.
All right, guys. So last time we did section 3.6, actually 3.5, 3.6. We did a little out of order. We talked about logarithmic functions and the person with a nice writing. Thankfully, has added a few things up there. I think it's probably Jenny that she's in here right before me. She can look there to see what's going on. Something like this here. I don't know if you all can see this. So if I did the derivative of the natural log of f of x, for example, what rule would come into play?
Would it be like the rule of ln, I guess?
Okay, good. But that's
chain rule.
Chain rule. I like it. The chain rule says take the derivative of this as if that was just x. And then you multiply by the derivative on the inside, and you can just plug that on top. So you could certainly memorize that, but to me it's almost too much memorization because you don't need to memorize it. You know the rule, so you don't have to make it a separate thing to memorize. It's the rule that is underlined. So you could memorize a ton of shit for this class, and that would drive me insane. And there's no way you would make it through math because there'd be no room left before you get very far. No room. I gotta go do something else. So I'd rather I know the rule, so I don't care. I mean, I can make it. What if there's a sign here? I can make a rule for that. What if there was something else there? I can make a rule for that. Well, why? But if you want to, it's there. Sure. Of course it's there, because the rule tells me it's what it's going to become. So I'm not going to memorize that. It's crazy. Any questions from homework before I... Look, he's like a brand new eraser. Almost. High-tech eraser. 66? No. Was there a question?
Yeah, 66 and 3.5.
3.5. Ooh, yeah, I like it. Blah, 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 blah. So two curves are orthogonal if their tangent lines are perpendicular at every point where they intersect. So for example, if I had a curve like that, and then there's a curve that comes in like that, and this was right there, their tangent lines are perpendicular, I would say that these two are orthogonal to each other.
Orthogonal.
Orthogonal, yes. So you have the idea of perpendicular.
Right.
Which we actually capture that as the word orthogonal means the same thing, but we use it in certain other situations, but they actually sort of mean the same thing. And then you have the idea of normal, and that kind of plays in tangent, and the normal is perpendicular to the tangent. You with me? So all these words kind of reference the same idea. I know, orthogonal is just too cool. You can make that in everyday. Dude, it's orthogonal. Maybe not. Maybe that won't catch on. It's totally orthogonal. Who the hell are you? Get away. So 66. So it says, show that the given family of curves are orthogonal trajectories of each other. That is, every curve in one family is orthogonal to every other curve in the other family. And remember, orthogonal is their tangent lines are perpendicular where they meet at their intersection. So on 66 they give you this. Can somebody tell me what that would be if I drew it? A circle, and its center is not what?
0, 0.
Is not the origin. I love it, because if I pull that over, I could complete the square. It would be moved somewhere as long as A is not 0, right? Or if A were 0, this would just be actually two lines like that. It's kind of weird. And the other one is x squared plus y squared equals by. Kick-ass. I like it. So what you need to do is obviously part of this is showing that the slopes of the tangent lines, which means I'm going to have to take derivatives. But also the other part of this is that it only has to be perpendicular where they meet. So the other part of this is figuring out where do these two things meet.
So don't you just set them equal to each other and that's where they intersect?
How do you set them equal to each other?
Well, x squared plus y squared is equal to x squared plus y squared.
Which doesn't tell you anything. And you're not really setting, this whole thing is what this is. So you're thinking back, if I could solve for y, and I say, where do these two meet? I can set these equal to each other because I am replacing y with what it is, right? So really, if x squared plus y squared equals ax and x squared plus y squared equals by, I can replace x squared plus y squared with by. Now you're starting to maybe get somewhere, right? So there's two parts to this, just like there's two parts to the idea of orthogonal curves. They are perpendicular to each other, that's one thought. At their points of intersection, that's the other thought. So it's the two parts of this problem you got to work on. Right? The derivatives should be relatively easy. Figuring out where they meet would be a different thing. But let's see if you play around with that. And you might even want to give yourself some specific examples, like if it was x squared plus y squared equals 4x. And if it was x squared plus y squared equals 4y, let's just make it like that. What would this would, if I suck the 4x over?
Y equals x. Oh.
Just working with this equation. You guys with me? And if I complete this square, what would I put here? Oh shit, do we remember how to complete the square?
4.
Yeah, half of -4 is -2, squared is 4. If I add 4 here, I better add 4 there. So now I get x minus 2 squared plus y squared equals 4. That's one thing. Now, where did I get this from and this from? I just gave a and b a value so I can kind of investigate, which is really an awesome idea when you get these freaky problems towards the end of the problem set to have a's and b's and k's and all this crap in them. Just give them values and look at what it is. Don't take too much away from this because this is a specific situation, but at least you can kind of see, well, when I make a change, then this is going to happen. So if I made a change, then what two things would change? If I made a, 6, then this would have been minus 6x, that half of that would be 3 squared is 9, that would have been a 3 there, that would have been a 9 there. So it would have shifted further right, and the radius would have gotten a little bit bigger.
So it changes the x value.
So right now it's going to be, where's the center going to be? 2, 0. At gather point, a little that's the center. And then from there I'm going to count how far out? 2, because the radius, this is r squared. So then my circle's going to look like that. Or, it's more like Stewie said, but oh well, they always do for me. Either Stewie standing or Stewie laying down. If you know who Stewie is, I don't know what to make of you. So here the same thing, right? Add 4, so now this will be the same idea, except it's going to be shifted where? Up. It's the same way that if it's inside of the letter, it's the opposite of what this says, right? So this would be up to, this is going to be the same thing, up to in the y direction. So this would be here. That's going to be its center. And it's going to count out to the same way, right? Out to, out to, out to, out to. Just getting there really quickly. So what do you think? See where they intersect? Does that make sense? Where they intersect, it looks like it would be perpendicular. Very good chance of that. So, I mean, this at least gives you a concrete thing to have in your brain as you try to attack this. Now, where is it that they meet? They meet at x equal to 2. So they meet at 2, 2, and they meet at 0, 0. Right? So how would I get that from this? I don't know. So, I mean, if you did take 4x equal to 4y, that doesn't really tell you. It just tells you x equals y, right? You guys see where I got that?
Yes.
Yes, ma'am.
Are you getting the 2 from the x minus 2 squared? Is that the point that
Oh, yeah, exactly. Yeah.
Oh, okay.
So the center is going to be shifted 2 to the right and then not at all up and down.
Right.
So that's why this circle is there.
Okay.
And the radius is 2, that's r squared. And same thing here, except it's shifted on the y-axis up 2.
Okay.
I like it. So x equals y, but does it make sense? And aren't these 2 points on x equals y? Aren't they? I like it. So if that's where those two meet.
Oh, so the line, are you saying there's a line between those two?
True.
points?
So this is not good enough to tell me where they intersect. Where they intersect are certainly on this, but does this tell me where they intersect?
No.
No. Which is okay, because normally when I have a system of equations and I do one thing, and then I have to plug it back in, don't I? So if I know x must be y, does it matter which one I plug it back into?
No.
Because I've set them both equal to each other in a way, right? So try it. Plug x equal to y. So replace x with y. Don't also replace y with x, or else you're not going to go anywhere. Right? Now do everything we're doing, but do it for them. But this was a really good place to start. It kind of made it a little more concrete as to what the hell was going on. And then I went, oh, that's what they're saying. It does make sense that this is where it bottoms out. So they would be perpendicular to the tangent lines. The tangent line for this guy would be like this, and the tangent line for this guy would be like this. That is perpendicular. That's enough. I'm going to let you guys go from there as much as you can. I'm almost certain that's further than anybody got, maybe. I don't know if anybody finished that problem. Because that is a neat problem. I love that problem. And you're all like, you would. All right. Yes. Okay. Oh, man. No, I want ice cream. Oh, yeah. Okay, go. Let's see. Blah, blah, blah. Ooh, that's yummy. So semicircle with diameter PQ sits on top of a cone.
What number is it?
54 in 3-3. What's up? Which one did I assign? It was 50.
I don't think you'll sign that one.
That's all right. She can ask me anything she wants. Oh, WebAssign. Okay, yeah. Because WebAssign doesn't let me do everything. All right, so here we go. Blah, 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 blah. Oh, they actually call it an ice cream cone. I love it. So if A theta is the area of the semicircle, and B theta is the area of the cone, or the triangle. It's only 2D, Jeff. Oh, okay. And they tell me a few other things. They better tell me what the hell theta is, and theta references this. So as I decrease the size of the cone, what's going to happen to the poor little semicircle? Small. Its radius is going to have to decrease, so it's able to still be a semicircle, right? So if I made a real skinny, it'd be like a jet. What the hell kind of ice cream? My radius would have to get really tiny just so it can fit again, right? I don't want that little. And they also tell me this is 10. These sides here are 10. And what they want me to figure out is what's the limit as theta goes to 0. Of course, from above, of the area here and the area there. So, what do you think is a really, really, really good idea to figure this out?
Divide.
Well, you can't divide.
Well, no, the limit, theta approaches 0 from A, and limit.
But you can't. I don't have something to work with, so maybe that'll lead you in the direction of what I'm trying to say. I don't have something to work with there, do I? I need something to work with, so I got to actually figure out what this is. Right? There's some kind of expression for this, or some kind of, and that's why they give me these. Maybe you guys are.
So do you actually put pi r squared over 2 and then for the cone?
So help me out here. Can you guys tell me what this is?
The right triangle.
Primary distances of
Depending on theta, right?
It's going to be like rule of cosine? We have two sides in it.
Well, you could do this, and then it's a right triangle, right? Or you could use law of cosines, because you have the included angle between two sides, right? I like it. Not a bad idea. But that's what it was really good. So you guys are like, well, start to look at the limit, and you got nothing to work. You got shit here. You got nothing to work with. So that's the first thing you do is, can I write an expression for what this is? And the funny thing is, the minute you know what this is, if it's 5 theta, let's just make something up, then how do I figure out the area of this? Its radius is going to be 2.5 theta in that case. You guys see what I'm saying? And then you'll know what the area of that is. It's half pi r squared.
So I know that I gave you all cosines, but it's just I didn't know what it's that.
Oh, well, don't try to do that.
Like, and then I tried doing the right triangle thing to it, and I was like, I don't know.
All right. No, the law of cosines is not a bad way to go. It's perfect, actually. It'll get you to a good place.
What am I supposed to expect? So something that looks like, say, 5 theta, or will it be?
No, you can't, you should know by now, you can't go into this kind of problem expecting anything. You really can't. You don't know what to expect, but you do know you just have to get what this is, some expression for it related to theta, which really, the nice thing is the minute you get what you need to figure this out, you'll have what you need to figure that out. And then you'll have expressions that you can work with as you let theta go to 0. Okay, so your intuition was correct. You're going down the right road. I think you were just trying to think too far ahead.
Okay.
It's just like those problems that say, show that it becomes this, and they give you the answer, and you're like, what I got doesn't look like that, because you're not done yet. Weird shit's going to happen by the time you get to the end, so you don't know what to expect.
All right.
Which is bad, because you're like, you don't know if you're in the right track, but I'm telling you, you are. I like it. Cool. So yeah, if you're on WebAssign does not give me every problem to assign. So I try to assign something that's on the same level of difficulty, but it will be different. So feel free to ask. Cool. I like it. Anything else from homework before we get back into it? Okay.
44 and
Oh.
2.5.
Oh, cool. This is another good one. This is exactly what I'm talking about. This is a problem. They give you the answer, and it's not going to look anything like it until you're almost to the end. Sorry, 44.
3.5.
3.5, yeah. So it says, show by implicit differentiation that the tangent to the ellipse at the point x naught, so you want to find the tangent to the ellipse at the point x naught, y naught, is this. I like it. Sorry. Gross. So what people try to do, they look too much to this. It's not going to look like this necessarily until you get somewhere close to it. And it looks like all they did was break that up and blah, 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 but you just got to attack it. Right? So you do the implicit differentiation. It says use implicit differentiation.
Is the A and B constants? So
A and B are constants.
So when you do quotient rule, A and B go.
No quotient rule.
You do product.
You don't need product rule. Or you use the power rule and chain rule, right? So this is 1 over a squared times x squared. It's a constant. So it just comes for the ride. So what's the derivative of x squared?
2x.
2x over a squared. Derivative of y squared?
2y dy dx.
Good. 2y dy dx. And to not make it look too weird, I just put that over. See, they just come for the ride. They're just constants.
Equals 0.
If you did set up a chain rule, its derivative would be 0, and it's like extra work you shouldn't have done. Yeah, equals 0. Now solve for the slope because it's asking you for the tangent at that point. I love this problem, by the way. That's all I'm going to say, by the way. So make sure everybody gets a chance to try it out. But you cannot look at this until you're almost done with what you're doing. Solve for dy dx. Plug that in. Yes, ma'am.
Isn't x naught and y naught just like the initial?
No, it's the point. It's like at the point 1, 3.
Oh, okay.
Yeah, I know the not normally for sciences and physics especially is the initial whatever.
Oh, okay. So
But-
it's like a specific point in time.
They could have just called it x1, y1 or
Okay.
yeah.
And I also need 46.
Where are we at?
3.5.
36?
46.
46. Ooh. Sorry. Alright. So again, as I do, I'll explain what the idea is and then stop. So this one says, show that the sum of the x and y intercepts of any tangent line to this curve
Square root of c.
thank you, is equal to c. Right? You're like, that's obvious. Do I have to show work, Jeff? Sorry, it's not obvious. Don't feel bad. It's not just obvious. I don't know what to do for it. The nice thing here is, since they say this, find a specific one. It should. What they're telling you is it will work for any. So then come up with, just make up a specific one and work with it if you want to. That's one way to do this. Because if it'll work for any tangent line, you figure out one tangent line and then show it's true for that. They already said in the problem that it's true for any tangent line. Well, they said show it, so I got to be careful. But I mean, what's the first step in this problem?
Take the derivative.
Yeah. And how do I do that?
X to the 1/2, y to the 1/2.
And they don't say this, but obviously C, hopefully, is constant. So yeah, so x to the 1/2 plus y to the 1/2 equals, doesn't really matter. Take its derivative, right? And then you have the dy dx in there. Figure out the tangent, the slope of it. You with me? And if you do it, let's do it at the point, in keeping with the C, we'll do it at the point AB. So what's this come out to be?
1/2 x to the negative 1/2 plus 1/2 y to the negative 1/2 dy dx
Good.
equals 0.
Equals 0. So then dy dx, cool the 1/2 die?
Oh, awesome.
Subtract that, divide by that, so you get negative x to the negative 1/2 over y to the negative 1/2. Is that cool? I'll stop there for a second. So at the point AB. So what's nice is I'm sort of doing it at a specific point, but I'm not. I'm doing it at every point, right? And this point AB is a point that is where? The point AB has to be where?
It has to be on the tangent line.
Yeah, good. So one thing I know about these two is this is true. Because that point has to be on the line, on the function, right? So I'm trying to find the tangent line to this curve at this point. So this point must be on that curve. So this must be true. So I don't know if that's going to come in handy. Yes, sir.
But isn't technically that statement always true? The square root of x plus the square root of y is equal to the square root of c? Because any value, because you're putting it for every point, wouldn't that, like, c is always interchangeable?
What?
He's saying that it's kind of universal because x and y can be any variable, c can be any variable. You can put whatever variables in there you want, and it'll always be true.
No. So, for example, if I made C 4, then this is actually square root of x plus square root of y equals 2, right? And these are very specific things that will work for it. Very specific points will work. So in this case, the point 0, 4 will work, for example. So I think you're reading too much into this. They could have just put square root of c is just a constant, but yeah. They want to put the square root of c because c shows up later. It just makes it cleaner. So what is the slope at this point? So yeah, negative. Now be careful, these are negative, right?
Negative y to the 1.
So I can flip them. Is that cool? And so it's negative, the y piece is b, like I think is what you said. Negative rad b over rad a. So negative rad b over a. Either way, it's going to help me out.
So then you do the slope, or you find the slope. You do the.
That's the. What is that? That is
that's the slope.
That's the slope.
So it would be y minus b equals square root of ba, negative square root of b over a, times x minus b a. Yeah.
Sweet. Find that guy's x and y intercepts and show that they had to be c. That's all I'm going to do because it's basically done. There's actually not that much work up there, was there?
No.
But it's just such a weird sounding problem. But you just start to attack it. You know you have to implicitly differentiate. You just know it, so you do it. You do it. And then you say, shit, any tangent line, well that means you just use the point AB or x1, y1 or something that designates that it's not a specific point. Keep in mind that that point has to work in the equation. That might come in handy somewhere, I don't know. That's all I'm going to do for you. Yeah, you're really, really close to the answer. All right. All right. I hate Tuesdays and Thursdays. By the time I'm ready to lecture, it's time to go. Shit. All right. So let's see. Where did we leave off? We're about to get into 3.7. Say again?
We're doing inverse trade.
Oh yeah, we're done with it.
Oh, we're done.
Yep. You know, it would be useful probably for you to memorize those, but to be honest, I don't, and I don't make my 280 students have them memorized either. But some of them come in and have them memorized, so it's up to you. It's up to you if you want to memorize them or not. I don't personally, and I never make my students memorize something I don't have memorized. I just make them when I need them. So we're going to get into 3.7. And remember, what we did last time, just to help you keep things going, what is the, if I gave you this, you know, like 1 base pi of 2x minus 4, what's the derivative of that?
Would be
1 over.
Good. The derivative of any log
Is 1.
starts off as 1 over the argument.
2x minus.
But it's not natural log, so
ln.
ln of the base. I like it.
Times 2.
Yeah, good. Times the derivative of the inside, so there's a 2 there. Alright. Now here's something interesting. Here's something kind of weird about natural log. E's got some weirdness because it's the only function we know yet that is its own derivative. Right? Watch this natural log business. So what is the derivative of natural log? That's crazy. So now watch this. Take a second and do this for me.
1 over 7.
1 over
Right.
7 over.
7.
So it'll be 1 over 7x times
7 over 7.
times 7, which is,
1 over.
holy shit. Do you understand? What does that mean? What does that mean?
That the derivative of ln of x with any constant inside is itself.
So here we go. This means the slope at any point on ln of ax is the same as the slope at any point on ln x, no matter what a is. Make a 18 trillion to the trillionth power. And 18 trillion you're trying to go to cancel, just like the 7 did, right? So if I do it to this, what's y prime? It'll be 1 over ax times a. Bam, bam. So no matter what a is, it's the same slope as the basic ln function. That is weird. And I shouldn't be too surprised because e is kind of weird in a nice way. And so is ln. ln kicks ass. And another way to look at this is kind of the better way to look at it, actually, in a way. What's the property of logs when I have the inside multiplied?
Natural log. Yeah, that's natural log of X.
And what is natural log of A?
It's 0.
No, what is natural log of A? It is a
Constant.
constant. So what the derivative of it will be
1.
0.
0.
So the derivative ln, see, so that's why there's two ways that the A doesn't matter. It either dies after the derivative or dies during the derivative. Right? Somewhere that poor thing dies.
Death.
Happens. Cool. I like it. I like it. Alright, and we also talked about here we go. So we'll review here. Let's give you a problem that's not quite as ugly as what we did last time, but if you think about this function too much, it will keep you up at night. It was on my junior year math competency exam. They gave us this problem here. Thank you, Jeff. But we had to do a lot more shit with it. But just imagine, this thing is really weird. Any negative values of x can't have, I can't have negative 1/2, because then I'd be trying to take a square root of a negative number. Do you guys see? But then negative 1/3 should work. But most calculators, if you plug this in your calculator, it just won't have it exist below 0. And I'm like, no, calculator should exist, but it exists at very specific points, which is weird. Anyway, we're not going to look at it too much like that. I just want to take this guy's derivative. Who remembers how I take this guy's derivative? Yeah, they call this y. And then take what now?
The natural log.
Natural log of both sides, so then I get natural log of y equals x ln x. Then I take the derivative.
And that's 1.
Derivative ln y is...
Oh.
Do it again? 1 over y.
dy.
dy dx. And what do I have to use here? Product. So derivative of x is 1 ln x plus x times the derivative of ln. So I get 1 over y. So I get, let's see if you can do it. dy dx equals y times ln of x plus 1.
Yeah.
Is that good enough? No, because what is y? Y was x to the x. Alright, so there's a little cleaner example of a problem we did last time. Second?
Why did the 1 become an x to the x?
He multiplied it out. So y is x to the x.
Oh, yeah, distribute the y through. And the y is x to the x.
Okay.
Yeah. Cool.
That's it? It just looks funny.
I know, it looks weird. I totally agree. Alright. Okay.
What if you did it again? What's the second derivative of that? Is it like again?
So if you have this, here's the nice thing. The derivative of x to the x is this. So watch. So if and anytime I ask you to take multiple derivatives, this happens very often. You'll be like, I have to take the derivative of something I just did. So just take that and plug it in. So I have to do x to the x prime, right?
Yeah.
Plus x to the x times ln of x prime plus x to the x prime. Well, this and this I already freaking did.
Right.
Right? That happens so often on multiple derivatives. Which kind of makes sense. You have this repetition going on with some of these. So this guy's derivative is all this. And this will be x to the x over x. Is that cool? Derivative of ln of x is?
1 over x.
And you can simplify that, believe it or not. Yes, you can. You can simplify it. X to the x ln of x plus x to the blah, blah, blah. Yeah. What is x to the x divided by x? Kick ass. X to the x minus 1. Do not tell me it's 1 to the x. That's no. You have x is on the top divided by 1, so now you have x minus 1 x is on the top. X to the x minus 1. Freaky. Okay.
Yeah. Okay.
Alright, cool. I like it. That's one of my favorite sounds. Alright, let me think. So let's get into some new stuff in the little bit of time we have left. I know, man. So, section 3.7 finally brings us to applications in all the sciences, really. And it's just silly. If has anybody got to take physics in the future? Any physics? Oh, look at that. So if you got to take calc-based physics, I hope, the real physics, because the non-calc-based physics is like, just trust me, this is true. And the calc-based physics is like, we can show it's true, yay!
It's happening to me right now.
You are taking it now,
Yeah,
concurrently?
it's right now, but I don't know if it's like. Because the guy's like, I know they told you you would use calculus. You are not. And I'm like, what?
Who the hell's that?
Some guy from Southwestern, he's here for his first
Awesome.
semester here.
Okay.
I was like, what?
So the hardest part for me, I taught physics. I taught regular physics, and then I taught non-calculus physics, and that was hard because so much physics requires calculus. It's insane. And then I taught physics 100, which is like just talking about the concepts, and you can't do any math. And physics is a beautiful example of a place where you can never really learn it if you're only allowed to explain the idea. If you can't see the equations, you cannot understand it. You need both. You need to understand the acceleration. Even if it's going up, the acceleration is still down. You have to understand that, but you also have to understand and look at the equations that go with it.
Well, pretty much all he's doing is like relearn trig.
Yeah.
And
Well,
that's
trig
all.
is obviously stupid
Yeah,
important in
that's all he
physics.
said.
But calculus, okay, hopefully it's got it. There's certain areas there's no way around it. When you get to inertia
It's a free body diagram.
and momentum and
Yeah.
all right. Yeah, but right now you guys are doing this kind of stuff, right? And you got this here, free body diagrams, friction's going there, normal force is going there.
Yeah.
Yeah. I love that shit.
Not
Sorry. All right, enough of it. So what we got here, let me just throw up some examples. Here's some from physics, some very basic physics. Kinematics, just to make it sound hard. We've already done this. For some reason, S represents position. I guess because position, I don't know how to do that. So if this is my position, what's my velocity? Good, so S prime of t equals v of t. And how do we get acceleration? That's double prime of t, that'll be the acceleration. And I think I told you guys what the triple derivative was. Do you remember? Yeah. What'd you call it?
Wait, but isn't it, if you're looking at it from the Y perspective, would that be air resistance or no? So if it's something that's
Whatever provides the jerk could be different. Right, so if you're going through like different pockets of air or something, that could be providing the change in your acceleration. Does that make sense? So yeah, totally. Because the reason behind why this is there could be several. Like my old car was really old, and that was like an implosion. And so that's what provided the jerk there. Right? You could say it was just the guy driving, but. Or Steve Martin. All right. So there's some really interesting problems with this because in a single problem they'll ask you stuff like what's the velocity after 3 seconds? What's the acceleration when the velocity is 0? So you have to really know which function you're working with, and are you putting 0 into it or are you setting it equal to 0? What are you doing? So I have to let you guys try some of those problems out. Let's see real quick. So if I have S is this, yeah, cool. And I want to know, when is it at rest? This is the particle. When is the particle at rest? And you're like, I don't know what religion it is. No. Does it have a religion? I don't know. What's it called?
When velocity is 0?
derivative, set it to
Material.
Exactly. So at rest means when the velocity is 0. So you have to find the velocity, which of course is the, I like it, or dsdt, I like it, either way.
Oh, it's good, man.
3t squared minus 12t plus 9.
And then what do you do with that?
Set it equal to 0.
Set it equal to 0. So I still get too many people that plug a 0 in. That's not right. That would be what the velocity is at times 0. Right? Set it equal to 0. And if anybody yells at me because I'm making you factor, then I'm going to yell right back at you.
You could take a 3 out.
Yeah, kill the 3.
So it'd be t minus 4, t minus 1. 2 minus 3, t minus 1. Yeah, I was just testing that.
Yeah.
So what does that mean?
These are
It's at rest
the
at
rest
1
is-
second and
A time 1 and a time
Good. It's at rest at 1 second and 3 seconds. And more than likely, if I graph this thing, it's probably going to look, something like that maybe. So you can see there would be possibly 2 places for it to be at rest, right? Is that cool? Because if I graph the s, I can see the velocity. If I graph the position, the velocity would be which visually or graphically would be the slope. Cool. So wherever I see a 0 slope would correspond to those where it's at rest, right? Is that cool? All right. And then anything else freaky? Oh, what does it say? When is the particle moving forward?
Would that be
acceleration is positive.
the first and the second derivative are both positive?
Jerk.
Sorry.
Yeah, velocity is positive. That's all you need. If the velocity is positive, but the acceleration is negative, I'm slowing down, right? That's sort of like remember we talked about the economy's decrease is lessening, all right? Well, it's still going down. It's just not going down as quickly, and we're all hopeful it's going to turn, right? All right. So all I got to do here, and you've already got where it's 0. So I don't know if you guys remember doing stuff like this. It's 0 here and here, and you can figure out where it's. Or you can just realize this is an up parabola, right? The velocity is an upward-facing parabola, right? So where is it going to be positive? It's going to be positive out here, negative inside here. And I don't know if this puts any restrictions on t. I guess eventually they put it 0 to 5, but anyway, you have to look to see if they have like t's got to be greater than equal to 0. It doesn't have to be. You can have negative time. It just means that many seconds before something happened. It doesn't mean like negative time before time existed. 3 seconds before the Big Bang. No. That would be very difficult homework. All right, I spent way too much time on that. And the 2 seconds I have. Current. How much do you guys know about current? One time I was in the lab, I got to tell you the story because I'm waiting for my superpowers. And we were putting together this thing, and what it would do is it would drop this piece of metal, and every second it would have a spark go out because it had a huge voltage going across it. So a spark would go out, and then they would measure the distance. And of course, because it's going faster and faster, the little spark burn marks would be further and further apart. This is way back. So of course Jeff was helping us set it up, and I was new there, and I'm all like, "You got it all set up?" "Yeah," and I had 2 extra wires. I'm like, "I guess we don't need these wires." They turned it on, and I had 40,000 volts go across me. And there was like a whole classroom full of students in there. So I'm like, whoa. And the students were all, and nobody did anything. I'm like, somebody kick me, somebody do something. And eventually I dropped, and the thing fell, and that's what cut the connection. And thankfully it was, anybody work with electricity? If you work with electricity, 40,000 is getting pretty up there, but thankfully the current was limited. If the current had not been limited, I could have very easily not be here right now. be in somebody's flower pot, maybe. Little Ash Jeff. So I used to go in every now and again in that lab and like say, "Watch the lights." And the students saw me, look at me. Here's that guy. It was awesome. All right, I've taken up all the freaking time. So, if you want to come over to 53541, it's right on the other side of campus. I'm going to go there right now.